Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with another math tutorial. Today we're talking about trig identities and how to use trig identities to simplify trig expressions. This will be the first of a two-part series. In the second part we'll talk about proving or verifying trig identities. So let's get started. Let's first talk about what an identity is. So I've got two equations here, two simple Algebra 1 equations that we can solve. And if we solve the first one, we would be adding 8. We've got 3x equals 12. We would divide by 3 and we get x equals 4. So for this equation, it's called a conditional equation because it's only true for a particular value of x. It might be a single value, it might be multiple values, but it's not true for all values of x. Let's look at this one. So on the right side, we could distribute and combine like terms, and we get here 2x minus 6 equals 2x minus 6. We've got the same expression on both sides, so this is going to be true for all values of x. This is called an identity, meaning the two sides of the equation are the same for all values of x. In trig, we have a set of basic identities which we will use, and we'll use these identities either to prove other identities and or to simplify expressions. We've talked about some of these earlier in the year. So these are called the reciprocal identities. So each of the trig functions has a reciprocal relationship with one of the other trig functions. So cosecant and sine are reciprocals. Cosine and secant are reciprocals, and tangent and cotangent are reciprocals. When we were using the unit circle, we had a definition for the tangent, which was y over x. And we also, when we were using the unit circle, y was the sine of the angle and x was the cosine. So we have here a definition of the tangent where it equals the sine of the angle over the cosine of the angle, and cotangent is the reciprocal of that. We also have a Pythagorean identity, which you'll be working on in an activity in class to show that this is true. But one of the most well-known and common identities is this Pythagorean identity. So if we take the square of the sine and the square of the cosine of a particular angle and add those together, that always equals to 1. If we divide this equation all the way across by cosine squared all the way across, so if I divided this by cosine squared, I would get here the tangent squared, 1, and that's going to equal, if I take the reciprocal of that, the secant squared. So this other identity that I have here is a version of the same Pythagorean identity. And again, if we divided everything by the sine squared all the way across, we would get this identity. So these are all these are the Pythagorean identities. And then when we have even and odd functions, and we could also figure these out from the unit circle, but if the sine function and its reciprocal and the tangent and its reciprocal are odd functions, meaning if I take the sine of, say, the negative of an angle, I get negative the sine of the angle. The cosine of, say, negative 45 and the cosine of 45 are the same. And here they're the opposite. So these functions are what are called even functions. So we may be occasionally using those identities. Most of the work today will be using these identities at the top. So we've got two kinds of problems to work. Our first kind is we can be given limited information about a particular trig function and find all the remaining trig values by using the identities. So here we're given the secant, and we're not told what the tangent is, but we're told that it's positive. And we're supposed to find the remaining trig function, so we have to find the other 5 trig functions. So the first one we can find is the cosine, because it is the reciprocal of the secant. So this is going to be 1 over negative 3/2, and we take 1 over something as the reciprocal, so we have negative 2/3. Now we can find the sine. To do that, we have to use the let me just put here, this is the cosine, so we can circle it so we know when we found all 5 items. We can use the Pythagorean identity, so sine squared of u plus cosine squared of u equals 1. And we just found the cosine, so we have sine squared of u plus negative 2/3 squared equals 1. Sine squared of u, I keep putting equals there, plus, this would be 4/9. Subtract the 4/9, so we get 5/9. And now we have to square root both sides. Now the problem here is when we square both sides, whoops, that's just now going to be get rid of the square if I square root, I've got both a positive and a negative possible value, which is going to be plus or minus the square root of 5 over 3. Now I have to decide, do I want to use the positive or the negative value? Since the tangent is greater than 0, that tells me that the sine over the cosine using the quotient identity has to be greater than 0. And we've already found that the cosine is negative. So we know this is negative. So to make this to be positive, the sine has to also be negative. So we want to pick the negative answer here. And again, that is the sine. And from that, we can derive using the reciprocal rule, we can get the cosecant is going to be the reciprocal of this. So it's going to be negative 3 over radical 5. And we can't leave it with the radical on the bottom. We have to rationalize. So the cosecant here is negative, that's a 5 here, negative 3 radical 5 over 5. So that's the cosecant. And now we just have left to find the tangent. So we just said earlier, using the quotient thing, the tangent is the sine, which we said was negative radical 5 over 3 over the cosine, which was negative 2/3. Now we have a complex fraction here, so we're going to turn that into taking the top and multiplying it by the reciprocal of the bottom. My 3's cancel out, and I've got negative times negative is positive. So my tangent is equal to positive square root of 5 over 2. And finally, the cotangent is going to be the reciprocal of that, so it's going to be 2 over radical 5, and when we rationalize that, we're going to get 2 radical 5 over 2. And again, that was the cotangent. So we've now found all 6 trig functions. We were given one of them, so we've got 1, 2, 3, 4, 5, 6, all the trig functions. Let's look at another one of these. Okay, so this time we're given 2 of the trig functions. Now we can use the reciprocal identities here to get the cotangent, was going to be 4/3, and the reciprocal of the cosecant is the sine. And we could find the cosine in one of two ways. We could use the Pythagorean identity that uses the tangent. So we could use 1 plus tangent squared equals the secant squared and find it that way. Or we can use the one that's easier to remember, is that the sine squared of u plus cosine squared of u. So this is the trig version of the Pythagorean identity, the Pythagorean theorem. So if I square this and subtract from 1, we get the cosine squared equals, that's going to be 9/25. So we subtract over here, we've got 16/25. And we square root both sides. Square root of this is 4/5. And again, we have to decide positive or negative. Now the sine was positive and the tangent's positive. So if the tangent's positive, sine and cosine have to be the same sign. So we want to use the positive version here. So positive 4/5. So here we've got 1, 2, 3, 4, and 5. And our last one is to take the reciprocal of the cosine, which would be the secant, and that's going to be 5/4. So we can use our trig identities to find out the values of all of the other trig functions if we know one trig function and then know something about a second one, whether it's positive or negative. We'll skip this one. Let's look at here. Now we're going to be using some factoring skills later in this tutorial, so let's quickly review. So we've got two kinds of factoring here. Difference of two squares. So here, if you've got something squared minus something else squared, it factors into a plus b and a minus b. So remember, this is going to factor into x plus 1 times x minus 1. Here, the square root of that is 3x, so we've got 3x plus 2 and 3x minus 2. Down here, square root of both pieces, we're going to have 4x plus 7 and 4x minus 7. These are simple trinomials. If you remember, our factoring rule is we want to find a pair of numbers that multiply to equal -2 and sum up or add up to be, in this case, -1. So this one's going to factor into x minus 2 times x plus 1. So those two numbers multiply to be -2 and add to be -1. Here, I need both numbers to be the same sign so that when we multiply them, they give us +6 and they add to be -5. Here, since this is negative, I need opposite signs, so this one's going to be x minus 6 and x plus 1. Common mistake here is to mess this up and use these two numbers, but it doesn't work up here because those two numbers have to be the opposite signs for them to multiply to be a negative. Now we're going to simplify trig expressions, and there's not really a specific procedure that works every time. This is something that you're going to need to use and learn by experience. So these are just some of the things that we'll try. We won't be trying these on every problem. We may use one of the identities to substitute in for one of the items in the expression, trying to get all of the entire expression, say, into all of one type of trig function. Sometimes we want to put everything in terms of sines and cosines. We will have expressions that have fractions, and we'll want to add the two fractions to get a single term by getting common denominators. We may have fractions that we can simplify by factoring and canceling. Special kind of substitution that we talked up here will be the Pythagorean substitution. And finally, we may have to multiply fractions by sort of the conjugate of the denominator to create a Pythagorean substitution opportunity. So let's look at these. We'll be using these skills as we go through the examples. So this first one, we may want to convert everything in terms of sines and cosines. So we can, the secant is 1 over the cosine, and the cotangent is the cosine over the sine. We can use fractions here to cancel numerators and denominators, so we get 1 over the sine of u, which can be simplified to be the cosecant of u using a reciprocal identity substitution. Okay, let's look at this one. Now we can use a Pythagorean substitution here. So we're going to use the Pythagorean identity here, 1 plus tangent squared of u equals secant squared of u. In fact, let's just, instead of solving this for tangent squared, let's just do that substitution actually over here. We just got to remember to distribute our minus sign. So I'm replacing secant squared with 1 plus tangent squared of u. And I'm going to distribute my minus sign. So this is going to become plus when I multiply through here by the minus. Now I've got tangent squared minus tangent squared. Those are going to cancel each other out, and I'm just left with -1. So this expression equals -1 no matter what angle we're using. And over here we could, if we evaluated the cosecant of u and evaluated this expression, since these are identities, we're going to get the exact same value. 2 more. So let's convert this to sines and cosines. Now we've got a fraction here, so I'm going to put this over 1, and we want to get a common fraction, so we need a common denominator. So now on the top I've got 1 minus sine squared of u over the sine of u. And if we look at our Pythagorean identity, if I solve that for cosine squared, by subtracting the sine squared, I get, so now I have cosine squared of u over sine of u. Now I'm going to do something here. Since I don't have sine squared in the bottom, I'm going to split the cosine squared into cosine times cosine. And this one will be times the sine of u. So now on the left I've got cosine of u, and using the quotient identity, this is cotangent of u. So that would be our simplification for that problem. Okay, here we've got one here. We're going to FOIL this out. So we're going to multiply sine of u, plus cosine of u times itself. So we can't just take this and be sine squared plus cosine squared, which would equal 1. We have to FOIL this out. So sine times sine is the sine squared of u. And we're in the middle, we're going to get 2 terms where we've got sine times cosine and cosine times sine. So I've got 2 sine of u cosine of u, and plus cosine squared of u. Now we can group those together, and that's going to equal 1 by the Pythagorean substitution, Pythagorean identity. So now we've got 1 plus 2 sine of u cosine of u. And that's as far as we can take that one. Kind of, you don't always know when you're done. You just keep going until you hopefully have something simpler than what we started with. And there's nothing obvious to do. Now here we can factor the top, because this is a difference of two squares, so we can factor the top into tangent of u plus 1 times tangent of u minus 1. Now what might trigger you to do that is, one, we've got something on the top that is factorable. It's a difference of two squares. And we have a fraction that we would like to try to simplify. So now we can cancel factors. Now remember, we can't cancel this tan with this tan or that one with that one, because you can't cancel when you've got things that are added or subtracted. So here I've got two things multiplied on the top in a division. Then we can cancel. So now we end up with tan of u plus 1. And now our last example here. This one's a little trickier. Let's just let x equal the tangent squared of u. So if I do that, I've got here x squared plus 2x plus 1. So this was, I noticed this because I've got even powers here. So this power is half of that power. So when I have that pattern, I can turn this into a polynomial that looks like that. And this factors into x plus 1 times x plus 1. So now if I replace the x with my tangent squared, well, actually, let's go ahead. This is x plus 1 squared. Now x is really tangent squared of u, so now we've got tan squared of u plus 1. And this is the secant squared, one of the Pythagorean identities. And that's squared, and something squared, we multiply the exponents, so we end up with secant to the 4th power of u. So in class we'll be working some more examples, and I've got an online practice gizmo that you'll be using, and hopefully you'll get, if you stick with this, you'll get good at being able to simplify these expressions. So have a great day.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you